Hello everyone, I'm Srijan from UNC Charlotte. Today I will be presenting limited data, unlimited potential. This is a work done at UNC Charlotte in collaboration with Stony Brook University and ViTs Hyderabad. So let's see, where are we with computer vision? We are going beyond object detections and can precisely localize object boundaries in scenes. This is an example of semantic segmentation using swing transformer. Similarly, now we can generate high quality videos using generative AI and vision language models. We are going beyond solving problems in datasets and actually implement these algorithms in real world scenarios, like we have Amazon Go, elderly monitoring, waiter robots, and many more. So, what are the reasons behind this success? Deep learning? That's not good justification in 2023, 2024. Here we present some results of three complex computer vision tasks: image classification, object detection, and semantic segmentation. We find that the results with CNNs are usually at the bottom in these graphs. And on the top results are with networks using vision transformers. So how do we use vision transformers? We first patchify the images into non-overlapping patches, flatten them, tokenize them through a linear projection. Then these tokens are fed to transformers to learn the global context. These transformer operations are exactly the same as what we use in NLP. Over here, we can see the results of different variants of vision transformers on different datasets with varying size. So tiny transformers, when trained on medium-sized dataset, they are not effective compared to if they are trained on large-scale datasets like JFT. Thus, the limitations of vision transformers are that they require large-scale data distribution for training. What if you have small-scale data? We can use these pre-trained models, and they're usually very effective on small-scale datasets. For example, an ImageNet pre-trained model, when fine-tuned on CIFAR dataset, yields 99% accuracy. But what happens for data which are quite different from natural images? For example, medical images. An ImageNet pre-trained model will not be effective on medical data. So let's discuss another trending mechanism in computer vision, that is self-supervised learning. What is self-supervised learning? It's a way to learn representation from unlabeled data so that it can be used for several downstream tasks. SSNs can help learn the structure of the data. The question is, can we use it for learning better representation on labeled data? So, does SSN improve ViT performance? So here we present the relative classification accuracy on three datasets with different sizes. Oxford Flower, which has 2,000 samples, CIFAR dataset where we have 50,000 samples, and ImageNet 1K where we have 1.2 million samples. Note that SSN in fact is not helpful when the scale of the data is very small and underperforms a standard model trained from scratch. On the other hand, our proposed self-supervised auxiliary task consistently outperforms others on all three datasets with two different backbones. So what is self-supervised auxiliary task? It is a simple, straightforward technique of training self-supervised learning jointly with the primary task like classification or segmentation. Although SAT has been explored in the vision community and robotics community, there are still many open questions, especially when the size of the dataset is limited. At inference, we threw away the branch with the auxiliary task and we can just use the primary stream. So let's elaborate the training process for an image classification task using SAT, which is self-supervised auxiliary task. First, we inflate the batch of input samples with two sets of augmentations, where one set of augmentation involves masking a part of the image. Then we fed it to our ViT, which has two streams, primary and auxiliary. The primary stream contains the transformer encoder or classifier head and hence performs the classification. Whereas the auxiliary stream performs an auxiliary task, which is self-supervised. What is the self-supervised task? It is masked image modeling. That means we feed a part of the image to the encoder. The auxiliary stream consists of a transformer decoder, which reconstructs the masked image batches from 25% of the input. Thus, the entire framework performs a primary task, that is classification, and a self-supervised auxiliary task, that is reconstruction. This framework can be jointly optimized using a convex combination of the losses from the primary task and self-supervised auxiliary task. In the experiments, we present the classification accuracy on the small size data sets with different variants of Bayesian transformers. In this table, we demonstrate the impact of using SAT while training the transformers for learning the class labels. All the models have been trained for 100 epochs from scratch. Although the models with SAT have more training parameters, they have identical operations during inference. SAT improves the classification accuracy on all the datasets for all the transformer encoders. The highest classification accuracy is achieved with CVT, which is a convolutional transformer. Given that, we recommend that the use of SAT to enhance representation learning in transformer training, it is reasonable to question whether this approach can lead to overfitting on small training samples. To address this concern, we evaluate the performance of our trained models on perturbed versions of the data. Our results demonstrate that ViTs trained with SAT exhibit greater robustness to these natural corruptions compared to the baseline ViTs. Similarly, we also compare SAT with the normal way of using SSN plus fine-tuning method of sequentially training ViTs. We find that SAT approach remains superior, requiring 26 GPU hours less training time and burning approximately 2.8 kg CO2 equivalent. However, the SSN plus fine-tuning model outperforms SAT when a large amount of training data is available. The next question is, which SSN should be used in SAT? We find that mask image modeling is effective as the auxiliary stream compared to contrastive methods like SimCNR and distillation methods like Dino. Finally, we perform experiments on domains with limited data. We find that SAT significantly improves the baseline accuracy. Also note that this SAT can overshoot the performance of ImageNet pre-trained models without using any extra data. Here we show ablation for the loss scaling factor, how SAT improvement is consistent across longer epochs, and how SAT improvement is consistent across different fraction of data. We also perform a state-of-the-art comparison with other representative ViTs designed for small-scale data training. We find that our method outperforms on existing baselines. We also find that GradCam visualization of SAT clearly focuses on areas corresponding to the entire primary object. We have also assessed the efficacy of the SAT within the video domain for the task of deepfake detection. The primary task involves binary classification to distinguish between real and manipulated videos. Our findings reveal that our SAT models demonstrate a superior generalized capability than other representative baselines. So, to conclude, we present a very simple, straightforward method to train ViTs on small data sets. The core idea is to jointly optimize the primary task with SSN as an auxiliary task. It is effective across 10 image classification datasets, 2 video datasets. And if you plan to use ViTs on small training sample, consider using SAT. Thank you.